these conformations can get a little more complex. In order to examine that, let's look at butane. We're going to look at butane drawing Newman projections by looking at it from this angle. So I've got a butane ball and stick model right here. And so we're going to be looking at it, not from this point of view, but from this point of view, starting at the second carbon looking through the third carbon. Okay? So we can see that. So let's draw some of these Newman projections. So first one I've got, you should be able to see that a little bit, is I've got on the front carbon a methyl group on top, hydrogen to the down and right, and a hydrogen to the down and left. On the back carbon, I've got a methyl going straight down and hydrogen sticking out between. Okay? So let's draw that Newman projection. So I'm going to start with front. So remember, I've got that methyl group on top. So it's going to be CH3. I don't need to draw out the whole thing. I can just write what's represented there. Then I've got hydrogen and hydrogen. Okay? In the back carbon, CH3 down below, H. Now we learned last time that this is called a staggered conformation. So let's go ahead and look at some of the other ways that this can go around, because the addition of these methyl groups is going to change things. Firstly, if I look at how this spins, when it gets to its first eclipse, I can see I'm going to have a little more interaction than just the hydrogen to hydrogens that I had before. See, I've got this big electron density that's now pushing away from this hydrogen. It's going to have a little more energy than it did before. Okay? So let's draw that. So again, I'm going to keep my top the same, my front carbon the same each time. Now I've got an eclipse here. Okay? We should see that. So I've got an eclipse, but I could turn this again, and I could have a different kind of staggered conformation. If I look at this, these methyl groups are now really close together, and that's a lot of electron density near each other. So even though this is a staggered conformation, it is a unique conformation. It has a unique energy level. And so let's draw that with this one. Let's draw that right. I'm going to draw that right here. CH3 still on top. And my back carbon has that CH3 right next to it. Okay? So we can see this is a staggered conformation, but it's a little bit different. We're going to have a bigger energy change right here. It doesn't matter if I move this back over here, it's still going to have that similar distance. Okay? And we'll give this a name in just a sec. But I want to take a look at the fourth type of conformation I could have here, and that's when these methyl groups get fully in line. You see, I can't even fully move the ball and stick model along it. So now my methyl groups are both pointing up. This is a lot of interference that's going on here. And so when I draw it this way, let's draw it right here. I'm just drawing these a little off to the side, but just remember these are eclipsed. So that's going to have a much bigger energy change. And so I've got really 4 different types of conformations I can have here. So let's give each one of these a name, remembering that these are both staggered types of conformation. And staggered is always going to be lower than eclipsed. So I'm going to write that these are staggered It's going to be those two. Specifically, this one will just get the regular name staggered. But this one gets a different name. This gets a new name. We call this a Gauche conformation. Weird word, Gauche. Okay. Now let's name these over here. Let's go red this time. So these are eclipsed. This type right here, just like normal, this isn't going to have a special energy level. So this is still going to just be called eclipsed. This one over here is going to be called totally eclipsed. So let's rank the energy levels of these. First off, I'm going to have low to high. Room? I don't really have room. Let's go over here. So we'll call this lowest down to highest. So the highest would be the least preferred because it has a lot of internal stress, a lot of internal energy pulling it apart. The lowest is going to be the most stable. So our lowest conformation, our lowest energy conformation is going to be our regular staggered conformation. Next, our Gauche conformation is going to be a little bit more. After that, we'll have eclipse. Finally, totally eclipsed. So this is our ranking of our energy levels. And in order to look at these more specifically, let's graph out what this would look like as it's rotating around. So here I've got this graph rotating around this butane molecule. So I've got it here, and then it rotates up to its first staggered conformation, down to its first Gauche, to its totally eclipsed, to its second Gauched, second eclipsed, back down to its fully staggered. So when we're looking at this, when we're looking at this energy chart, first thing I want to notice is that both versions of my eclipsed are higher energy. And both versions of my staggered are lower energy. So if I'm trying to figure out what's my lowest energy configuration, I know for sure that it is going to be one of these staggered conformations, whether that's Gauche or staggered. Either one of those two, okay? So I know it's not going to be any kind of eclipsed conformation. If I'm looking at the highest level of energy, I know it's going to be some type of eclipsed. And it's going to be where are my biggest groups and when do those overlap? That'll be pretty simple. But we'll be able to use this idea to figure out the lowest energy. So let's go ahead and label these. So this is my staggered. Let's go right here. This is my number 1. This is staggered. Then number 2, let's use red for our high energy. It'll help us keep track of it. Number 2, this is eclipsed. Number 3, this guy right here, is Gauche. Number 4 is total eclipse. So after that, we go back to Gauche, eclipse, staggered, and repeat the whole process over. I'm going to be able to use this idea to tell me what's going to be the lowest energy configuration for something. In order to do that, in your workbook, I've given you a graph similar to this, but it's got specific energy counts labeled. These won't always be the same. However, what will always be the same is this general pattern. Our Gauche conformations are going to be the second lowest energy conformation, and our fully staggered conformations are going to be our lowest. So let's use that idea to figure out another molecule's lowest energy. All right, I've got a similar example set up in your workbook, but I wanted to go through this on the board so that we could see kind of why we're figuring it out the way that we do. For each of these conformations, we're looking at the same molecule. We are looking at a 2,3-dimethyl butane. And this 2,3-dimethyl butane has these three potential staggered conformations. What we want to know is what's the lowest energy? What's the lowest energy conformation that it can make? We already know that none of the eclipsed conformations are going to be the lowest energy, no matter which way we point it, because those will always be higher energy than the staggered or the gauche. So what we need to do here is figure out how many gauche configurations do we have? Because technically speaking, this methyl group being this close to this methyl group is going to be a gauche. And there's no point in here where I don't have something similar to that. So what I really need to do is count how many CH3 groups are near each other. And this would work the same way if I had more than just a methyl group. I could have a couple ethyl groups. I could have some hydroxide groups. Those are all potentially gauche conformations. I could look at any one of those the same way. But I'm really looking at how big is that electron cloud. Okay? We're not going to do anything too complex here. We're really just going to be looking at how do I tell what the lowest energy is. And so this right here, I'm going to count 1, 2, 3 interactions where I've got methyl groups right next to each other, right? So this is gauche, this is gauche, this is gauche, okay? This one here, got a similar situation. 1, 2, and 3. So this is gauche, gauche, gauche. Technically, these two are staggered from each other in the same way these two are staggered from each other, okay? So we could label that. Let's do purple for that. So I've got these two are staggered. I've got these two being staggered. Now in this third one, if I look at where my gauches are, I've got one here, but then nothing there, and one here. So there's one gauche, one gauche. And how do my staggareds look? Here I've got a staggered, and here I've got a staggered. So this one has fewer gauche configurations, which means it has fewer of these slightly higher energy interactions. And so this one is going to be my lowest energy. So in your workbook, I go through and I actually apply the numbers, the actual joules per mole, I think it is. But here, I just want you to see the principle behind this is really just the number of gauche conformations, okay?